Hello everyone. I'm really excited to share about our work BALM, a model-agnostic framework for balanced multimodal learning under imbalanced missing rates. To start off, multimodal learning relies on combining complementary input sources, for example, elevating language, audio, and visual information for sentiment analysis tasks or different types of scans for medical segmentation. However, in a real-world scenario, sensor failures, recording noise, or high acquisition costs mean we are frequently dealing with incomplete multimodal learning, where certain modalities are missing. Beyond data incompleteness, models inherently suffer from modality imbalance, where certain modality dominate optimization due to signal reliability and so on. And when missing modalities occurs during training, this imbalance significantly worsens. Previous works typically simplify incomplete data problem by assuming a shared missing rate, where every modality drops out with the approximately same probability. But real-world data degradation is rarely that clean, and so we instead focus on the imbalanced missing rate condition, where each modality is absent with different probabilities. Under imbalanced missing rate, even existing models built for addressing incomplete data exhibit severe performance fluctuations and show clear signs of learning imbalance. So, following these observations, we want to answer the questions of enhancing existing model robustness via addressing two coupled challenges introduced by imbalanced missing rate. The first challenge is representation imbalance, where heterogeneous missing patterns distort unimodal feature distributions, and the second one is learning imbalance, where gradients are heavily dominated by a modality, leading to bias convergence. Our method is a plugin framework that includes two core components, the Feature Calibration Module and the Gradient Rebalancing Module. During training, features pass through Feature Calibration Module to handle representation distortion. The calibrated features then feed into any standard multimodal backbone. Here we describe a multimodal emotion recognition backbone that includes modality-specific encoders, a fusion mechanism, and a prediction head. Concurrently, lightweight unimodal prediction heads and the gradient rebalancing module is plugged to monitor gradient dynamically. During the inference, these auxiliary components are omitted, leaving only a feature calibration module active along with the backbone. This ensures our framework introduces minimal computational overhead while requiring zero changes to the existing backbone architectures. First, let's look at the feature calibration module, which handles the representation level imbalance. The primary goal of feature calibration is to establish a shared, stable representation basis across modalities despite heterogeneous missing patterns before the data even enters the main fusion backbone. Instead of explicitly generating or imputing missing raw signals, a feature calibration module leverages global contextual cues. It first aggregates the available unimodal features into a global descriptor, then it extracts cross-modal dependency and maps it into adapted calibration grades for each modality. Finally, the weights are used to rescale the features. Next, to resolve the optimization level imbalance, we use the Gradient Rebalancing Module. Its goal is to harmonize optimization dynamics to ensure all modalities receive fair and consistent supervision. To start off, we retrieve the fusion predictions and gradient vector from the main backbone to use as cue for monitor the optimization. For similar informations of each modality, we approximate them from modality-specific encoded feature via unimodal prediction heads. In the case of multimodal emotion recognition tasks, these heads would be multiple fully connected layers to mimic the overall architecture of the backbone. For distribution-driven modulation, we use Kullback labor divergence to track the relative distribution progress of each modality. A modality-specific distribution that shows a high Kullback labor divergence to the main fusion distribution suggests its learning as being neglected and fails to align with global information. When this happens, its update is dynamically amplified via a supervision coefficient to bring it back on track. For spatial-driven modulation, multimodal optimization naturally tends to drift and follow the directions of the dominant modality. So, to stabilize training, we explicitly reorient the gradient towards a balanced multimodal direction, which is the average direction across modalities. This modulation is introduced as an additional test via a regression loss built directly upon the cosine similarity between the fusion and unimodal gradient vectors. We evaluate the effectiveness of our method on the multimodal emotion recognition test using two conventional data sets, namely EMO-CAP and CMO-Mosaic. To simulate real-world settings, the data sets are masked using a stochastic operation drawn from a predefined missing rates. The robustness of the multimodal emotion recognition backbone, including MMGCN and MMDFN, after plugging our framework as reported across entirely different missing rates configurations using downstream test measurements, specifically the accuracy and weighted F1 score. On EMO-CAP, our method clearly elevates the performance of the integrated backbone and raises their performance low bound to above 60% score for both accuracy and weighted F1. You can also see the performance lift can be seen on CMU Mosaic. We also elevate the shared missing rate configurations to prove that our method works on both types of missing modality configuration and therefore it is effective in addressing incomplete multimodal learning in general. Our ablation study also showed that both modules fulfill their balancing goal. To summarize, in this work we propose BALM, a lightweight and model-agnostic plugin framework combining Feature Calibration Module and Gradient Rebalancing Module to mitigate representations and optimization imbalance, addressing the missing problem from training phase. Our future works may include extended experiment on different benchmarking tasks and improving the techniques for mitigating representation and optimization imbalances. And would also include more detailed discussions on the effect of specific missing ratios.